Up here, one is what do you get when you mix a strong acid with a strong base, and basically at the neutralization point they both annihilate each other. So the only thing you have driving the pH would be the neutral salt, which pH is going to be neutral. Nothing going on there. Number 3, what about if you have a weak acid and strong base at the equivalence point? Okay, those are both going to be gone, and you look on the product side. In this case, your salt actually is going to be the conjugate weak base of this weak acid, and so it's that conjugate base that's going to drive the pH, so it will be slightly basic. So this one, and you had an attached sheet that had a whole bunch of pKa and some Ka and some Kd values. So the question here is, how do I make a buffered solution? Not just any buffered solution, but a buffered solution where the target pH is about 2.7. And this is one of the things I mentioned in lecture. We're going to use the Henderson-Hasselbalch equation. And remember, we want this ratio to be about 1 to 1. And if this is 1 to 1, the log of 1 you guys told me 0. So kind of if somebody ever asks you to do this, basically your target pH needs to be the P function of your Ka. Okay? So you can look on your options there, and I picked a couple. I picked a couple. I don't think I wrote them down here. But what I did was I said, well, what Ka are we after? So we can get to the Ka by taking 10 raised to the negative pKa. So 10 raised to the negative 2.7 power is 2.0 times 10 negative third. So these pairs actually, if you look up H2Te and H2SeO3, you're going to find that the Ka is ballpark, is the closest I can see. Okay, so the next one. Okay, oh yeah. So not bad on this one, I thought. My husband and I would kind of compare notes sometimes and I thought you guys did pretty good. So switching it up from the autoionization of water to the autoionization of NH3. So if you have 2 moles of NH3, excuse me, one will be the proton donor, one will be the proton acceptor. So the product side, you're going to end up with NH4 plus and NH2 negative, which we didn't, I don't think, necessarily thought about. That's what you end up with. Then the next question, if we're going to write the KAM, that being the ionization of ammonia, then remember the equilibrium constant expression is the product, molar concentration of product times the stoichiometric coefficients divided by the molar concentration of the reactant. But the reactant's a liquid, so it doesn't show up in our, that would be a KW expression, it's a KAM expression. And then down here it said, what if you know that KAM, which is like KW, right? What if we have a value of 1.0 times 10 negative 33rd? What will be the pKam? So any P of anything is applying the log function. So just make the log of that. And you're looking at 2 sigma A to be 33.00. But if you put 33, that's fine. This time. And then the question is, what's the molarity of the ammonium ion? If it's neutral at that same temperature, it's weird to be dealing with something that's negative 35 degrees Celsius, but you do what you gotta do, make it a liquid. So this is kind of what we looked at a minute ago with water. We know that the molar concentration, if it's autoionizing, the NH4 plus, that molar concentration is going to be equal to your NH2 negative concentration. So I just said let X be equal to the molar concentration of both of them. Then in our expression becomes whatever that KAM is, which is 1.0 times 10 negative 33rd is equal to X squared solved for X. And that's the molar concentration of actually both of those ions, but specifically the ammonium. And then the last one, or E, what is the PNH4? And see, I put the little pluses because I think it should have. But anyway, what is applying the P function to this value? So apply the P function to this body. And you get 16.5-ish. And then what would be the relationship between the PNH4 plus and the PNH2 and the PKAM? And they have a kind of a similar thing as the PKW is equal to the pH plus the POH. But I guess when we do pH, we don't do pH plus, do we? POH, we don't do POH minus. So maybe so. It just seemed like they should be on there. So now this one, KOH is a strong base. HCN is a weak acid. And so ask some questions. Oh, it goes to form KCN and H2O. So the Bronsted acid on the left, anyway, the proton donor would be your HCN. Well, I guess it's not an equilibrium arrow, so it's only going one way. So HCN is your acid donating proton. OH minus is your, or could be KOH or OH minus is your accepting proton. The salt formed on the product side is the KCN. Conjugate acid-base pairs, we've got two of them, the OH and H2O, and the HCN and the CN minus. Spectator ion, and actually there's two of them, but I just put one because I still don't agree. This is where my tiredness is coming out. So my husband Carl, he's like, he put the CN, the thiocyanine ion, as a spectator ion. No, because how can it be conjugate base and spectator? So anyway, I just put K plus, and I think you guys did too. The last one, then, kind of related question: what's the weak base? And that would be the conjugate of the weak acid, so CN minus. All right. So this one was a titration curve of that you guys did the other day. And it should have kind of this, if you're going titrating a weak acid with a strong base, it should have kind of this weird sort of slopey thing in the bottom. The equivalence point is the inflection point, you can see there, and I think I picked it as 22, I think maybe somebody picked it as 20, but anyway, either one's fine. But from there, when it talks about where is pH equal to pKa, that's your half neutralization point. So whatever you put for A, you divide it by 2 to get to B. The region where the pH depends primarily on your excess base. So that would be after the equivalence point, so anything greater than 22 milliliters, or 20 milliliters if that was your equivalence point. For D, where are you going to have your HB, which is your weak acid that you're titrating into, which region are you going to have it where that actually is greater than the conjugate that's being formed as you drip in base? And that's going to have to be before your half equivalence point. So actually D and B are related, so less than 11 milliliters. And then the last one, I kind of took some whatever kind of ranges, but where would you best likely have a buffered solution? I take anything between the beginning of the titration and the equivalence point. A buffered solution just means that you have weak acid, in this case, and its conjugate base present. All right, so this one, you can kind of see what a lot of times working a problem, if you put on blinders before you go to work the problem, it kind of makes it easier. Ammonia is a designated weak base. And actually, if you kind of look right next to it, NH4 plus is I put conjugate weak acid of the weak base. Then we actually have formic acid is a weak acid, and then below it, this guy right here, the CH3COO negative, that is the conjugate base of the weak acid. Then we've got a strong acid, an HCl, a strong base, and KOH, and then KCl, that's going to be neutral. Not much chemistry going on there. So with all of that in mind, which would have the highest pH, and I still sometimes I've caught myself that it says highest pH. I want to go with the highest pH would be the most basic, not the most acidic. So that's going to be a strong base, KOH. What I started to say is I think highest pH, highest hydrogen ion concentration. That's not right. Highest pH actually is the lowest hydrogen ion concentration. So for B, what would have the lowest pH? Your strong acid HCl. neutral will be the KCl. For D and E, they kind of go together. In both of these cases, I wanted them to be near neutral, but just a little bit off of neutral. So the one that's going to be basic, but near neutral, is not going to be your weak base. It's going to be the weak base conjugate of your weak acid. Okay? Because put another way, your, let's see, what was the weak base? The NH3? The NH3 is going to be farther from 7 than this one. Okay? So it's your HCOO minus that's actually going to make it basic, but less basic than NH3. Similarly, down here, I wanted something acidic, but close to pH 7. So you couldn't put the formic acid because that would actually be more acidic than NH4 plus. So look for that settle from there. And then the last one, which would have the highest hydronium ion concentration, of course, that's your strong acid, HCl. All right. This one, in bold, says that the reaction that I gave you here is going to occur. It's just gotta. So we have a strong acid, a strong base, and you can see underneath those two, I've written down the volumes and the molar concentrations. And your question is basically to knock out what the pH, OH, hydrogen and hydroxide ion concentration is. So I call it counting beans. So we need to know basically which one's going to be in excess. I'll just put it that way. Which one's going to be in excess, how much in excess, and divided by the volume. The total volume up here is going to be 39.2 milliliters. So counting beans, I kept it in millimoles. With regard to millimoles of HCl, you're looking at 11.4. NaOH, you're looking at 7.36 millimoles. Now, the fact that they react in a 1-to-1 stoichiometry means I'm like, dude, I know that I'm going to run out of NaOH first. So that kind of showed me how I need to proceed. So basically, all I need to know is how many millimoles HCl are left, and then divide that by your volume. So I can get to millimoles of HCl that were consumed by using millimoles of the limited reactant, which was NaOH. So of course, 7.36 millimoles of HCl were consumed. We started with 11.4, so we must have 4.0 millimoles of HCl remaining. So like I said, then it becomes just a point of taking those millimoles of HCl and divide it by the total solution volume. And then one last step to get from molarity of HCl to molarity of H plus. So when I went to grade this one and some other ones, if you made a key mistake but got all the rest right, then definitely possible that you kind of got more points. So this is to say that if your H plus didn't come out right, then your OH minus and your pH and your POH wouldn't come out right either. But I didn't hold that against you. All right, on this one, what is the pH of this solution? So we need to kind of concentrate on what is that solution? Of course, that's acetic acid. It's a weak acid. And a weak acid will ionize to just a certain extent like this. So this goes back to when we did equilibrium constant expressions, and we need an ice table. So we have an initial molar concentration of your unionized CH3COOH, its conjugate base, the CH3COO negative, that's the acetate ion, and the H plus. And in our ice table, of course, we have minus X plus X plus X, and these are equilibrium concentrations. Our simplifying assumption says that we're going to assume that X is going to be significantly smaller than the amount of the weak acid we started out with, which is 0.4. Then that 0.4 minus X becomes just simply 0.4. So that's nice. 0.14 minus X becomes 0.14. We solve for X, and you're looking at 1.6 times 10 to the negative third. Of course, that is your hydrogen ion concentration. So we can knock out pH by applying the negative log. All right. Then on to this one. So there's, this is definitely, there's two ways to make a buffered solution. This is the easier of the two ways. And we know it's buffered because you have, well, it says buffered. You have NH3 and you have its conjugate acid. So you have a weak base and weak acid of a conjugate. You know what I mean. Different by a proton. So the information given is the pH of the solution is given. So here's the Henderson-Hasselbalch equation. So the pH is given. We're going to have to get to pKa. I'll show you how we're going to do that because we have to massage the information out because Ka is not given because NH3 is a stronger weak base than NH4 is a weak acid. So we're going to have to massage that out and then log the ratio of, and I went with molar concentration of base to acid. So just to make sure we're all on the same page, the base is the NH3 and the acid is the NH4 plus. So I mentioned we have to kind of massage the pKa out of what we know about the Kb of NH3. So the Kb of NH3 is given. We can get to the Ka of NH4 plus this way by plugging in that Kw divided by Kb. And so that's the Ka we've got. So we need to go ahead and get to the pKa, apply the P function, and then 9.25 is what we're going to plug in right there. So then we have the log of the ratio of the base to the acid. And this is where you can see how I did it. I went ahead and did my subtraction, kind of rearranged a little bit. So I know the pH, the pKa, kind of bring the pKa over to the pH, and you're looking at -2 is equal to log of the ratio. Now, in the problem that was given, we know the ammonium concentration, but we don't know the ammonia concentration. I wish they called those things two different things, ammonia and ammonium. I know I've mentioned that before, but really? So to get to that, we're going to take 10 raised to the powers. And so 10 raised to the negative 0.2 is equal to 10 raised to the log of a quantity is equal to that quantity. So life becomes a little easier. Go ahead and resolve this as 0.63. I crisscross, so your ammonia concentration is 0.098 molar, or thereabouts. All right. So this one, and this one seems like it should have been worth more than 6 points because that's a heck of a problem. But from the problem, I can kind of see how I laid out the information that we know. This is at the equivalence point, so the significance of that is we have a weak acid and a strong base, and you should try to be thinking at the equivalence point, they're all used up. So what's driving the pH, we're going to have to calculate down here, actually is the presence of the CH3COO negative, that acetate ion that's making it basic. So notice that the molarity of the NaOH is not given, but you don't need it because it's at the equivalence point. But you do need the volume. So you can see up here, I went ahead and knocked out what 25 plus 31.4 is, because that's our total volume. We're going to need that later. So it becomes one of these problems where all we got to do is get to the molar concentration of the acetate ion and then go from there. So how are we going to get the molar concentration of acetate ion? Well, it's at the equivalence point. We have volume and molarity of the acetic acid, and then we can get to moles from there, and then use stoichiometry to get the moles of the CH3COO negative. Okay, and then we just need to divide that by our total solution volume, which is 56.4 milliliters. That's why you need the volume of NaOH. So that's the molarity of that conjugate weak base we're dealing with. So what's the weak base going to do? It's going to do this. It's basically going to abscond on from a hydrogen from a water molecule, and in doing so become acetic acid and then create that hydroxide ion. So it's that hydroxide ion that's making this basic. So we run into another problem though. As I've written this right here about the acetate ion, actually that's a Kb expression, not a Ka expression. So there is no Kb given for acetate, but there is a Ka given for acetic acid. So you have to kind of reverse engineer that. So to get to Kb for acetate, we have to take Kw divided by the Ka for acetic acid. think I said that right. So we're going to use that in our problem. So we need an ice table. In our ice table, we have the molar concentration of acetate ion. Initially, no acetic acid or hydroxide. Negative x plus x plus x. Simplifying assumption is applied, assuming that x is significantly small relative to the molar concentration of the acetate ion. Then this term actually becomes essentially 0.122. Plug into our Kb expression now. Kb is equal to the molar concentration of acetic acid times the hydroxide ion divided by the molar concentration of the acetate ion. Solving for x, you end up with x is equal to 8.2 times 10 negative 6 molar. Now again, part of working any sort of problems in physical science is laying out so that you remember what the x is. X is the molar concentration of the hydroxide ion. So we can knock out, I guess we're trying to go for pH, there's different ways to skin this cat, but we know we can get to the hydrogen ion concentration from the hydroxide ion concentration by dividing the Kw by the hydroxide ion concentration. And now that's a hydrogen ion concentration. We can use the pH by applying the negative law. Okay? So, there you go. That's the last page.